Okay, let's take a look at this differential equation. Any dE that appears in this form, I would check first if it's exact. Uh, by now, you've probably seen a few and worked on a few that you can quickly see this is not exact, right? So, step one, check if it's exact. Oh no, sorry. Pencil was acting up. So that's M and that's N, and partial y of m is 1, and partial, which is not equal, again, I don't even need to write this, but because we get 2, right, with respect to x, because y the fourth is a constant. All right, so there is a trick. If it meets a certain criteria, we could try to get it to be exact. But this has to hold true. Okay, step 2. If it's not exact, so what we often call shorthand, like this m partial y, we call it m sub y, and this is n sub x. Okay, so what you do is you check my minus nx over the original n, and if this is purely a function of x, that's an x, then we can get this to be an exact form. And if not, it's not all hope is lost, because this one we'll see that does not work. Or if you divide by m and you get it as a function of y, we'll use g. Okay, if either one of those hold, we can get this to be exact. If not, not going to work. Well, there actually might be more manipulation, but I'm not sure. I wouldn't waste the time. I'll try a different method. In fact, for this one, I'd still probably do a different method. But let's just see, like, can we proceed, right? My minus nx, I'll go ahead and use different color. So my, we had 1 minus 2 over n 2x plus y the fourth. That is not clearly a function of just x, right? Because we have this y here. So that's a no. Checking the other one though, again, remember, not all hope was lost over m, that's which is just y. Is that a function of y? Yeah, because we only get negative 1 over y. It will work. Okay, there's more steps, but it will work. I'm going to sidestep really quick. If I have this problem, this differential equation, and even though it's in the form where I check if it's exact and it's not, I'd probably take a quick second. Like, can I manipulate this guy to use a different technique, right? We've learned several other techniques of solving a differential equation. I would go for that. So let's move the y dx to the right hand side. So I'm just going to rewrite this as negative y dx. Okay. Always shoot for separation of variables. This one's, I don't see it's going to work. If we divide by that 2x plus y the fourth, right, and then move, no matter how you see it, this has a function of x and y, right, which is typically why we shoot for exact, because m and n are both functions of x and y. It's not going to work. However, not all hope is lost. Typically, we try to get like dy dx, right, because every form to this point we've seen y prime, dy dx, but we can think of dx dy and still use the same technique. So why am I suggesting that? It's because here, right, if I divide by negative y, we can, we can divide each of these terms by that y and then break this up. But if I divided by this 2x plus y the fourth on both sides, I would kind of be stuck, right? So let's go ahead and do that. I'm going to divide by dy and divide by negative y. Let's get rid of those little purples there. There we go. So we would get dx over dy equals 2x plus y to the fourth over negative y. All right, this looks good again because I can rewrite this as negative 2x over y and then minus y to the third equals dx dy. Okay, rearranging the terms, and we always prefer this dx dy or dy dx either way there because that's how most of the differential equation forms are through this point. And so I would have added the 2x over y. I'm going to write that like that, and you'll almost immediately see this equals negative y to the third. Right, that looks good because all I did is move this to the other side equal. Great. Now this is a linear first order differential equation, right? Because again, thinking the y prime plus p of x, y equals q of x, but you could think of p as a function p of y, right, and q of y, and then wherever there's y, there's an x. Just reverse them. So in that case, we need the integrating factor. So we need rho of y, okay? And remember that's p, we use p of x here, so we have 2 over y. You go e to the integral 2 over y dy. And that integral is just 2 ln y, e 2 ln y. And using properties of logarithms, e ln y squared, e and ln cancel, y squared. Okay, that is our integrating factor. And then the process, so at this point you should be comfortable solving linear first order differential equations. So I'm not going to explain it all. The process we get is that we have x multiplied by that integrating factor y squared. Typically it's y multiplied by the integrating factor, but again, we're reversed, equals the integral negative y to the third multiplied by the integrating factor y squared dy. Oh, and this side we're also integrating. I kind of threw that out there, but again, at this point, this should be review. Okay, left-hand side, we get xy squared equals integral of negative y to the fifth. So xy squared equals negative y 6 over 6 plus c. And, right, maybe we'll want to multiply by 6, maybe solve for x, I don't know. Really, depending on the technique you used, your general solution could vary, okay? But we can manipulate that to any form. In fact, probably want to solve for c because that's how the exact equations usually are written, right? We write f of some function of xy equals c. So we could compare at the end, but y to the 6 over 6 plus xy squared equals c maybe. Okay. I think you will see this process would be preferred if you can manipulate that differential equation, so it might be, worth a minute to try that. Moving back to here, to the left. I stopped there to pause, and the next step would have been finding an integrating factor if we had this, we'll stick with blue, the f of x, then our integrating factor rho of x would have been e integral fx dx. Okay, I'm not going to go through the proof of y, but the rho of y actually gets a negative, e to the negative integral gy dy. Okay, this video is long enough. We're not going to look at proving all this. That's just, it is what it is, okay? So, our rho is e to the negative integral negative 1 over y dy. So that's positive 1 over y, and integral of 1 over y is ln. So we get e to the positive ln y, which is just y. All right, step 4. It will, by default, if all this holds up to this point, by default, we will get the differential equation in exact form. I want to go ahead and show that really quick. So the next step, we multiply the original function by this integrating factor. Okay, so the original differential equation. So our new differential equation becomes y times y dx, so y squared dx plus, we'll go ahead and distribute the y, 2xy plus y to the fifth dy. Okay, that is our new differential equation, and therefore the m and n, right, they're not the original m and m and n. We typically, notation is m bar, n bar. But you could see now, partial m bar, partial y, is 2y, and partial n bar, partial x. So only treat x as a variable. So again, this is 0. X is a variable, so 2 and y are constants. And we get that partial is 2y. So we're good. All right. Next step. So I guess that's step 5. That's our partials, because we will need that, is to start getting our function here. And so step 6, I explain this exact the exact form in another video, so I'm not going to explain every piece of it here, but what we're basically doing, right, very briefly, is constructing this differential equation by knowing that our function, like I said over here, is a function of x, y. I look at this original m bar and n bar, and I'm like, oh, that's the easy piece, right? N bar, maybe it wouldn't be terrible integrating with respect to y, but I like the left. So what we are going to do is take our function x, y, and again, either one you want to do, but what we're saying is if we integrate the y squared dx, what I'm missing is some sort of function of y, which kind of makes sense because when you integrate, right, you need to add some constant anyways. But I know it's a function of y because of this dy here. Okay, so we're going to integrate the dx and then derivative and then integrate again. All right. So let's go ahead and go back to the blue, I guess. All right, now again, we're integrating with respect to x, right, dx. So this becomes xy squared plus our function of y. Okay, step 7 now. So we have this should be equivalent to n here. Let me gather my notes really quick. N bar, which we said 2xy plus y to the 5th. Oh, yeah. Okay, I see. All right, so we know that this is f, but I know that if I took derivative with respect to x, I would get n bar. All right, so that's what we're looking at. We're taking this partial f, partial x on both sides. I probably should have done that in purple, but that's okay. Partial x, partial x, because then I know that that is equivalent to n bar. Oh, no. Oh man, I'm losing myself here. We need, so we just integrated with respect to x. That wouldn't make sense. We need to integrate, or we need to partial with respect to y. Okay. So let me erase that. Okay, and seeing this, I think will make better sense anyway. So with respect to y, we'd have 2xy plus some function of y, its derivative, right? So why is that n bar? Because this dy here, right? Like we integrated the first with respect to x, and now derivative with respect to y, and that should be equivalent to n bar. And why else that makes sense is after you've done a few of these, which apparently I need more practice, you will see part of it is always equivalent. Okay, this 2xy, those are going to cancel. So therefore, g prime of y is y to the 5th. Well, derivative with respect to y, derivative of function g of y. Right, so what we do is we are going to integrate with respect to y. That way we know what our g function is. And we get 16y6 plus some constant g. And why is that important? Because we had our function f above. I should have wrote this as another line, but remember f was this, xy squared plus g of y. So therefore our function of xy is that, right? Xy squared plus g of y. But we know g of y now, and we're also going to use that fact which is said over there, f of xy, or function of xy, can always be written as a constant. Our general solution can always be written in that form. So, final step, xy squared plus g of y, 1/6 y to the 6 equals c. Phew. It worked. We actually have the same result, right, that we did over here. Lengthy process, but same result. I noticed I quit writing those steps. 7 and 8, oh man, those always throw me off. But anyways, we had our f, right, and then 8th was to actually find our g prime. And then last, like, write your solution in the general solution form, f of xy equals c. There you go. Again, like I sidestepped right at the beginning, right? Like, that is a lot of work to get it to be an exact form. When it's not, try something else. Okay, I much prefer the first part of the video doing it in that method.